A couple of you guys had an older set of notes before I fixed this error. I want to go ahead and make sure that everybody gets this fixed for future reference. So I didn't find this before I uploaded the notes at the beginning of the semester, and then I did find it later. So this is back in urinary system. It was incorrect on an old version of the notes. It should say the ascending loop actively pumps solutes, sodium primarily, into the ECF, and then the descending loop is permeable to water. So will you look at page 8 of your urinary system notes and fix it right now if it needs to be fixed, and then realize that I probably won't nitpick you about it because it was incorrect in your notes. So I'm not saying I'm not going to ask anything about this, but I probably won't ask you the difference between the ascending and the descending loop, right? The big picture is still the same, right? The big picture is still that you pump ions into the extracellular fluid, right? And then water follows out of the tube, right? And a longer tube does that more. I just had the loop parts flipped. Everybody okay with that? Okay, so we are going to finish respiratory system today, and then we'll have a couple minutes at the end to finally give you your third test back and just go over the short answer. So everybody okay with this? I can close it? Yeah? Okay. Oops, that's one too. So I think, trying to remember where we were. I think we were right here with external respiration, and we just watched the video. Does that sound right? Okay. So this stuff is not too bad today. I don't think it's too bad. And we will probably finish a couple minutes early so that we can have time to look over these. Okay, so what we watched the video last time that was basically showing you that respiration, the process of gas exchange, occurs primarily down partial pressure gradients, right? And which is analogous to concentration gradients. Everybody with me on that? Before we go any further, will you guys, somebody tell me the difference between these two terms? What is ventilation versus respiration? Breathing, air in, air out. What is respiration? Gas exchange, exactly. Does that make sense? Okay, so what we're going to do now is just basically go through in the notes what we looked at in the video, right? And then we're going to add some detail to it, and it's not going to be terrible. So there's basically two different kinds of respiration. There is external respiration. External respiration happens at capillary beds, both pulmonary and systemic capillary beds. And then internal respiration is cellular respiration, okay? So just make sure that you slow me down or stop me if you get confused today, because most of it is pretty logical, but it's easy to get flipped around if you don't pay attention, okay? So two different stages of external respiration. The first stage of external respiration is at the pulmonary capillary beds in the alveoli. Everybody okay with that? Okay, so the gas exchange that occurs first between the alveoli and the pulmonary capillary beds. So we have talked about that before. So this is the respiration that occurs here, okay? So it's going to be exactly what you expect. The mechanism of respiration at the pulmonary capillary beds is really just diffusion, because oxygen just diffuses down its partial pressure gradient and carbon dioxide just diffuses down it. And that is important because it means that if you get blood and air near one another and they have a partial pressure gradient, then you don't have to worry about transporting. Transporting just occurs naturally via diffusion. So the site of transport, by the way, is referred to as what we call the respiratory membrane. And the respiratory membrane, guys, is this little teeny thin membrane that basically just has the wall of a capillary right next to the wall of an alveolus, right? It's super duper thin. It's about 0.2 of a micrometer, or 1/6000th of an inch. And there's so much of it that you do gas exchange super easily at your pulmonary capillary beds. So the respiratory membrane, you have about 300 million alveoli in healthy lungs. Of course, fewer if you have emphysema, right? It's going to like decrease the surface area. And that means for the average size person with an average size lung, you end up with about 750 square feet of respiratory membrane. And I have lived in apartments smaller than that, right? That's ginormous. It's about 25 feet by 30 feet. So tons and tons of surface area and tons really, really thin. So you get tremendous gas exchange. In addition, the lungs also have a disproportionate amount of blood in them at any given time because you've got 5-ish liters of blood, right? At any given moment, your lungs have about a liter percolating through them, right? So thin, right? Lots of surface area, disproportionate amount of blood equals really, really good for gas exchange. Everybody okay with that? Okay, so basically what you are going to do is the respiration process at the lungs is not going to surprise any of you. Basically, the blood that you are delivering to the lungs from ultimately the pulmonary arteries, everybody with me? That blood that is going to the lungs is going to be high what, low what? High carbon dioxide, high PCO2, right? And low PO2. You with me? Okay. All right. So then what we are going to do is the PO2 in the alveoli of the lungs is really, really high compared to the blood, just simply because we live in an atmosphere with a really large concentration of oxygen compared to what's actually in our bloodstream. So the PO2 is high in the alveoli of the lungs. And so what oxygen does, of course, if you deliver low oxygen blood right next to high oxygen air, then oxygen moves into the bloodstream, right? Logical, right? And then the carbon dioxide, before we get into carbon dioxide, the thing I want you to know is that not only does it move into the bloodstream, we will see that it also moves onto hemoglobin. Okay, so I want you guys to think of hemoglobin as an oxygen or a gas ferry or a gas bus, right? So here's what is going to occur at the pulmonary capillary beds. The oxygen is going to get onto the bus. There are 4 seats on every hemoglobin bus for oxygen. Are you guys with me? Okay. So it's going to get onto the bus. So when I, for instance, do the first step of external respiration between my alveoli and my pulmonary capillary beds, I am going to move oxygen first into the blood plasma, but then it's actually going to get onto the hemoglobin. And the vast majority of it is going to travel on hemoglobin. But logic question for you. Can I, for instance, take that oxygen bus, right? I'm going to deliver it back to my heart, and then I'm going to pump it to my systemic capillary beds. Can you use that oxygen for cellular respiration if it stays on the bus? No. You are going to have to make it get off of hemoglobin in order to be used for cellular respiration. So can you predict sort of what's going to occur? Basically, every time we go through my pulmonary capillary beds, the oxygen is going to load onto hemoglobin, get on the bus. And every time I go through my systemic capillary beds, it's going to get off the bus to go to work, unload off of hemoglobin. Does that make sense? You can do the same damn thing over and over again. Okay, so loading onto hemoglobin. So carbon dioxide for just a second. Carbon dioxide is going to do exactly what you thought it was going to do. Air has relatively low carbon dioxide. Blood being delivered to the lungs has relatively high carbon dioxide. It's going to diffuse into the alveoli, and then you're going to breathe it out, right? Exactly what you thought was going to happen. So basically, this is going to occur. And then the next step is obviously that now I have oxygen and low carbon dioxide. I'm going to deliver it back to the heart and then pump it to the systemic capillary beds for the next step of external respiration. Everybody okay? Okay. So I just did respiration at the pulmonary capillary beds. And then the respiration at the systemic capillary beds should be obvious to you how this is going to occur. So the blood that is ultimately coming to the systemic capillary beds was just in the lungs, right? Lungs, heart, right? So you can bump up the pressure and then deliver it to the capillary beds. And so that blood is going to be, the blood delivered to systemic capillary beds is going to be high PO2, low PCO2. Yes? Okay, and the tissue cells, again, just to reinforce what we were talking about, the tissue cells are going to be high PCO2 and low oxygen because they're doing what again? Cellular respiration. Damn concept won't leave us alone this semester. It just won't, right? So they're doing cellular respiration. Okay, so here is what is going to occur, and we'll actually look at the predictive factors for it in just a minute. But basically what's going to happen is the oxygen has to get off the bus, right? It has to unload from hemoglobin into the blood plasma, right? But then it can't stay in the blood plasma. It's actually going to have to move into the interstitial fluid and ultimately into the tissue cells, right? Okay, so this whole process is the second step of external respiration, and the whole damn thing serves this process, yes? Serves internal respiration or cellular respiration. Does that make sense to you guys? Okay, and like we said last time, the driving force for all of these gradients is cellular respiration because it's consistently generating carbon dioxide and using up oxygen. Yeah? Okay, all right, so now what we are going to do is we're going to talk in detail about how you transport oxygen and carbon dioxide in the bloodstream, okay? And it's going to be fine. So basically, you guys know already that the primary mechanism that you use to transport oxygen is you transport it inside the red blood cell on the hemoglobin molecule. So at any given moment, most of the oxygen that is traveling from point A to point B in the bloodstream is on the bus. 98.5% of oxygen that is carried at any given moment will be inside the red blood cell riding on hemoglobin. Does that make sense? Okay. So, and of course, putting this together with things that you've already learned, when oxygen binds to the heme portion of hemoglobin, what does it do to the color of your blood? Bright red. And why? Because it's oxidizing the iron. It's rusting your blood, really, right? Okay, so it's going to be bright red. They will call that, for instance, saturation, right? You are saturating, you've got a high O2 sat. So let's just look at this for just a second. Okay, so remember that each hemoglobin, which don't look like squares, but this is simplifying it for you, has 4 oxygen seats, yes? Okay, so do you see that this is 100% saturated? Yes? Okay, and you still have a few that are traveling in the blood plasma, right? Does that make sense? Okay, that might be true of systemic arterial blood. It's usually in a healthy person going to be close to 100% saturated. And why? Because there's so much oxygen in the air that it's really easy to dump it all onto the hemoglobin. Does that make sense? So all of these buses are full. Yes, they are all full of oxygen. This one is venous blood. Venous blood does not have 100% saturation of oxygen. I know that you guys are in the habit of thinking that venous blood might be 0 oxygen, but just so you know, it's not. You always carry around some. You just don't carry around as much as you had in arterial blood. Everybody okay with that? Okay, so here is what we are going to talk about. Basically, our hemoglobin, right, is an oxygen bus or an oxygen ferry, and it has 4 seats, right, for oxygen on each hemoglobin. And so what is going to happen is you are going to load them onto the bus. When you do that, blood bright red, it is called oxyhemoglobin. And of course, you are more likely to form oxyhemoglobin as you go through the pulmonary capillary beds, right? Right? You're going to form oxyhemoglobin. And then it won't do you any good if you don't ever let them off the bus. So what you are going to do in the systemic capillary beds is you are going to form deoxyhemoglobin, right? Oxyhemoglobin, deoxyhemoglobin, oxyhemoglobin, deoxyhemoglobin. So this whole process has to be loose and reversible, or else it wouldn't do you any good, right? It has to be able to get on and get off really easily. So here's what we are going to do now. We are going to look at the factors that determine whether you are going to load oxygen onto the hemoglobin bus or unload it. So here's a logic question for you. Everything that occurs at pulmonary capillary beds should favor, you choose, loading or unloading of oxygen onto hemoglobin. Loading. Do you see? Okay. Everything that is true at systemic capillary beds should favor what? Loading or unloading? Got it? Okay, so now that's our prediction, and all we have to do is go through and check off and make sure our prediction is actually true, okay? Does that make sense? So there are several factors that determine whether you load or unload, and hopefully these will make sense to you. So one of them, and we're going to go through this in your notes as well, but I just sort of want to look at it. The factors that determine whether you load or unload, one of them is just PO2. And that's probably okay, right? Your PO2 will determine whether you load or unload. What's your prediction? High PO2 will make you do what? Load or unload? Yeah, okay, got it. Okay. The other ones you might not be able to predict yet, so let's just go ahead and list them. The next one, I'm going to put this next. It's PCO2. Okay. And then the third one is pH. The fourth one is temperature. And the fifth one is one that you probably haven't heard of yet because I never see it in any other context. It's DPG or BPG. Okay, so here's what we're going to do. We're going to go through each of these and see if we can logically figure out, for instance, what would be true at a pulmonary versus systemic capillary bed. And then we're going to use that to predict whether, for instance, increasing PO2 or decreasing PCO2 will cause loading or unloading. And it will make sense if you just let it. Okay? You ready? All right. So these are the factors that determine whether you saturate or desaturate. So let me just go ahead and tell you, as far as terminology goes, loading equals saturation. You ever used one of those O2 sat monitors in which you got it like on your fingertip, or in babies they have one on their head? What happens is that is actually measuring primarily just by the color of the blood in your capillaries, how much oxygen is found in hemoglobin, right? Okay. And in a healthy person, you're going to have it 100 or close to 100, right? Okay. So loading is when you saturate oxygen with hemoglobin, which will make it, of course, or saturate hemoglobin with oxygen, which will make it bright red. Okay. Does that make sense? Okay, so let's go through each of these and make sure it makes sense before we move on to the next one. Okay, so in order to predict whether you're going to load or unload, let's look at the factors independently. If you compared PO2 between pulmonary and systemic capillary beds, yes? Which one do you predict would have a higher PO2, pulmonary or systemic capillary beds? Pulmonary. Everybody cool with that? Pulmonary capillary beds. So you guys predict for me before we look at it in your notes. If we looked at it, a high PO2 would cause, you choose, loading or unloading. What's your prediction? Yeah, that's what I would predict too, and that's actually what's true. And that is true at which capillary bed again? Pulmonary or systemic? Pulmonary. Okay, so here's what I want to do with this. What I want to do with this is every single time, let's choose what's true at pulmonary capillary beds. So all the factors are going to favor loading. And then you, on your own, could make exactly the opposite list for what is true at systemic capillary beds. Does that make sense? Right? So if you learn half of the prediction, you can do the other half of the prediction very easily. Okay? Okay. So PO2, our prediction was that the higher the PO2, the more oxyhemoglobin was formed. Yes? This is called saturation. So an increase in PO2 causes loading. You get on the bus, yes? Okay, for transport. And it's really, really easy to saturate oxygen onto hemoglobin because there's so much more in the air than there ever is in the blood. So there's tons and tons in the air, comparatively speaking. So where PO2 is low, however, the opposite is true. If the PO2 is low in a tissue, it tends to favor things getting off the bus. Desaturation or unloading, right? So that would be true at what capillary beds? Systemic capillary beds. You got the logic? Okay, so now let's do the next one. And again, I want you guys to make the prediction before I tell you. The next thing that determines, I'm going to do PCO2 before I do pH. The next thing that determines loading or unloading is PCO2, okay, independent of oxygen concentration. So let's think through this. Which capillary bed, systemic or pulmonary, would have high PCO2? Systemic would have high PCO2 because of cellular respiration, right? And so what do you predict about high PCO2? Is it going to favor loading or unloading? Unloading, exactly. So the opposite is true here, right? If we're keeping track of pulmonary capillary beds, then the pulmonary capillary bed comparatively would have what? High or low PCO2? Low. And that would favor what? Loading. Got it? Okay. Anybody not have it? Ask if you don't. Okay. Does everybody understand that you can very easily predict that the pulmonary capillary bed should have a lower PCO2 than the systemic capillary bed? Right? A, this is the source of cellular respiration, and B, you're getting rid of carbon dioxide here. Yeah? So you can see that prediction, that difference? Okay, all right. So that will lead us to this one, of course, right? Because we know the damn equation for carbon dioxide. I don't know how many times you're going to try to teach this to me, Melanie. You know I'm going to put this on your final, right? I'll make you do the same equation because you've learned it 4 times. Okay, so this is the equation that predicts the relationship between carbon dioxide. This is an enzyme called carbonic anhydrase, H2CO3. This is carbonic acid, which dissociates to H plus and HCO3 minus. Okay, so predict for me before I tell you which capillary bed, systemic or pulmonary, should have a lower pH. Sit and work with it for just a minute. Which capillary bed, systemic or pulmonary, should have a lower pH? Yes. And why? Because of carbon dioxide concentration, right? And if you increase H plus concentration, what does it do to your pH? Drops you down to nobody likes pH. We just have to get used to it. Stop resisting. You're like, stop it with the pH. I didn't make those rules. I didn't make it the negative inverse log of the concentration of hydrogen ions in solution. Okay, so let's try to figure out what would favor loading. So work with me here. What pH, low or high, should favor loading? High, yes. High pH, which is true in your pulmonary capillary bed. And it doesn't have to be high. We're just talking about relative to one another, right? Remember, the pH doesn't change very much. It's like 7.4 to 7.6 all, right? But if it's a slightly higher pH, you're more likely to pick up oxygen. If it's a slightly lower pH, you're more likely to drop off oxygen. Okay, so let's look at that relationship in your notes. So in low pH or acid situations, you're more likely to unload. The acidity is primarily due to production of carbon dioxide, also a little bit of lactic acid. So an increase in pH favors loading, and a decrease in pH favors unloading, right? Because that should be the difference between your 2 capillary beds, okay? So the way that my mind does this is instead of memorization, it tries to figure out comparatively what should be true in the pulmonary capillary beds, and everything that should be true there favors what? Loading, yes? What should be true in the systemic capillary beds? Everything that occurs there should favor unloading, right? So I like to work at it backwards, from the logic that makes sense to the memorization instead of from the memorization to capillary beds. Does that make sense to you guys? Right? Because it allows me to get some confidence with what I'm doing. Okay, with that in mind, let's do temperature, and instead of looking at the notes, let's see if you guys can predict, okay? Which capillary bed should be hotter, especially if it is metabolically active? Does that make sense? Systemic capillary bed should be hotter, and it'll get hotter still if it's really active, right? Does that make sense? And why? Because generally the air that you are breathing in is lower than body temperature, right? Okay. So what do you predict about temperature? As temperature increases, does it favor loading or unloading? Unloading, yes, so that you can use it. As temperature decreases, it favors loading. Does that make sense? So make this statement for me. What temperature favors loading? Lower temperatures, yes? Are you seeing the logic here? Okay. All right, and then the last one. This one's kind of obscure, and I have to build it for you for just a second, and then I will do a summary for you. Okay, so there is this chemical that is produced by red blood cells as a byproduct of their glycolysis. Okay, it's called DPG or BPG. I won't make you spell it out, but it's 2,3-bisphosphoglycerate or 2,3-diphosphoglycerate. Regardless, DPG or BPG is fine. So question for you. Why do red blood cells only do glycolysis and not go through oxphos? Any idea? Because what? Red blood cells do not do... See if you can... Yeah, they don't have mitochondria, right? So here's the deal with red blood cells. Red blood cells do not need oxygen. They carry it, but they don't need it. Yes? They're just the oxygen bus. They don't actually use the oxygen. Is that okay with you guys? Right? So here's the deal with red blood cells. Whenever their metabolic rate is relatively high for a red blood cell, they produce this chemical called DPG and BPG. What DPG or BPG does is pushes oxygen off the bus, because the red blood cell seems to say, if I have a lot of metabolic needs, then probably other tissues do too. Here, have some oxygen, right? So as the metabolic needs of any tissue in any area goes up, then you're likely to produce more BPG. And so as BPG goes up, does it favor loading or unloading? Unloading. So low DPG or BPG favors loading. And this isn't as obviously different at systemic versus pulmonary capillary beds, but it's obviously different in respiring tissues, right? It's tissues that are really active, right? You're going to generate more BPG or DPG. Okay, so let's do a summary and make it all sort of make sense. You ready? It's not as bad as you think. Okay, so in your systemic capillaries, see, I want you to make sure that these make sense as I go through each one of them, okay? If I compare my systemic to my pulmonary capillary beds, do these things make sense? Okay. In systemic capillaries, you should have lower PO2. Yes? Yeah? You should have lower pH. Make sure that one makes sense to you. Why? Yeah? Okay. Everybody okay with those two? You should have higher PCO2 in your systemic capillary beds. And the more active they are, the higher BPG you should have. Yes? All of those factors should all be true at a systemic capillary bed, and therefore all of those factors should favor loading or unloading. Unloading, yes? Get off the bus to go to work at systemic capillary beds. Yes? Okay, so let's do the exact opposite and make sure it makes sense to you. And if it doesn't, you should raise your hand and ask questions, because you're probably not the only one that has that question. Okay, so in pulmonary capillary beds, again, make sure you're checking this off in your mind and that it makes sense. Compared to systemic capillary beds, this is what should be true in pulmonary capillary beds. They should have a higher PO2. Good? They should have a higher pH. Why? So a higher pH, because they're blowing off carbon dioxide, right? And not generating as much carbon dioxide. Does that make sense? Okay. They should have a lower PCO2. Pulmonary capillary beds should have a lower PCO2 than systemic capillary beds. Good? And unless they're really, really active in cellular respiration, they should have a lower BPG. Yeah? And all of those things, if true at pulmonary capillary beds, should favor what? Loading or unloading? Loading. Got it? Okay? All right. So all of these are just little logic relationships. If I were you, I would do the opposite ones, except what I would do is try to figure out how to cause unloading without putting the arrows in until I think it through. Right? So try to figure out all of the factors and then think through what should be true at systemic capillary beds. Does that make sense? And that would be a really good check mechanism to make sure that you understand the logic between them. Can you tell that I don't memorize this stuff? I just think it through every single time, right? And if you don't memorize it either, you'll remember it for longer, believe it or not. Sounds counterintuitive, but if you memorize it, you'll lose it. If you learn it, you won't lose it. Okay. One last little thing to talk about that's directly related to this. It's kind of cool and kind of interesting. What does carbon monoxide have to do with our story? Carbon monoxide, the little bastard, is the one that sits on the hemoglobin bus, yes? But it takes up the seat of oxygen every damn time. It sits on oxygen's seat, and it has a greater affinity for the seat than oxygen. So this is like if anybody's ever ridden public transportation. So if you've been to New York and been to any other actual city that has a lot of public transportation, you know that on public transportation, buses and trains, they have a couple of seats that are reserved for people who are handicapped or disabled or pregnant women, right? This is the little 25-year-old punk that sits on that seat when there's a 75-month pregnant woman right next to him and stays on his phone, and he just stays there the whole damn time and never gets off. So here's what happens with carbon monoxide. If there is carbon monoxide in the air that you are breathing, when you breathe it in, it has a greater affinity for the heme than does oxygen. And it's not very reversible. It's hard to get it out of the seat. So every single time it goes around, your blood looks like it's saturated. Why? Because there is oxygen on carbon monoxide, and it'll make your blood bright red. But it doesn't get off the seat, and it doesn't supply cellular respiration. And then the next time you breathe in, you just breathe in more carbon monoxide, and it sits on the seats. By the time you die because of it, you are just circulating no oxygen, not letting anything off the bus every single time. Does that make sense? So that's how carbon monoxide poisoning occurs. It has a greater affinity for the heme group on hemoglobin than does oxygen, and it's not very reversible, right? So what happens in those situations is the person just gets really exhausted at first, right? You get super exhausted from carbon monoxide poisoning. Sometimes you're a little nauseated, and then you go to sleep, and then you just don't wake up with carbon monoxide poisoning. And the reason this is worth mentioning is not only is it relevant to the story, it's also relevant to us here in Utah, because most of us, of course, have homes that are heated not by electricity, but by natural gas, right? And carbon monoxide is a byproduct of burning fossil fuels, yes? It's colorless and it's odorless, okay? And it would happen if you didn't have proper ventilation with your natural gas heated home, right? So here's the misunderstanding that a lot of people have, and you guys probably already understand this. I'm not talking about the gas that comes out when you turn on your stove and it doesn't light. They put a smell in that so that you can tell that it's on, right? Carbon monoxide is burned fossil fuel, and it's going out in the actual ventilation system. If your ventilation system has a leak in it, then that is going to leak into your home, and there's no way to tell it's there, unless, of course, you have a what? Carbon monoxide detector. And it's really important for us to have them because, of course, the way we heat their homes, also those of us who have children, children are really susceptible to carbon monoxide poisoning, and they die relatively quickly of it. So make sure you got a carbon monoxide detector, make sure you test it, make sure if it goes off, you don't just take the damn battery out like you do with your smoke detector when you set your kitchen on fire for the 45th time. I mean, not that I would ever do that, but all the time. And then if you have kids, I always have two, because I have one outside the kids' room and one like near the source where it could be coming from. And they're a little more expensive, but definitely worth it. So that's carbon monoxide poisoning. I'm from Texas, and I like to make fun of Utahns, but we got rednecks. I'm pretty sure we had them first. So, so in Texas, for some reason, winter surprises people every damn year. Texas summers, everybody knows, are outrageously hot, right? But what you may not realize is that Texas winters are outrageously cold, and not pleasant, fluffy snow kind of cold, like hard sleet that just like is coming sideways at your head, and everything's unpleasant and gray. It's gross. But every single year, people forget that is going to occur, and they didn't check their heating, and then their house is freezing. But Bubba definitely has a barbecue, and Bubba will bring the barbecue into the house and light it to heat up the house with no ventilation. And then Bubba and Cletus and Crystal and whoever the hell is in his house, they all die because of carbon monoxide poisoning. Happened every single semester that I taught in Texas. Somebody knew somebody who died because of carbon monoxide poisoning, and usually because they brought the barbecue grill inside the house. So the lesson there is, do not be like Texans. Just generally don't. Except Austin. Austin's lovely. Amazing tacos. Okay, so now let's talk about how you carry carbon dioxide in the bloodstream, right? Okay, you with me? So we're switching from oxygen to carbon dioxide, Okay, carbon dioxide is more complicated. It's also kind of interesting to me. So how do you carry carbon dioxide in the bloodstream? Well, there's 3 different ways that it's carried. Oxygen is almost all on the hemoglobin, but carbon dioxide has 3 different ways that it's carried. So first off, so stick with me for just a second. It's going to be confusing at first. There's 3 ways that you carry carbon dioxide. Of course, if we start in the tissue cells, that's where it was generated, right, via cellular respiration. You carry 7% of your carbon dioxide dissolved in the blood plasma as carbon dioxide. So it's just in there as carbon dioxide. Everybody okay with that? Okay. The next one is you carry 23%, yes, of carbon dioxide on the globin portion of hemoglobin. This does not compete for seats with the oxygen, and that's important for you guys to understand. And I've mentioned this to you before. So you have 4 seats for oxygen, right, on your hemoglobin bus, but you also have separate seats for carbon dioxide. So what it does is it loosely and reversibly combines with hemoglobin, right, and just holds on to it, right? Does that make sense? Okay. So it's not out competing oxygen. In theory, couldn't you carry both of them simultaneously? So let's say you picked up oxygen with your hemoglobin bus, right, up here, and then you deliver it to your systemic capillaries. Does it ever happen on public transportation that people get on before the other people get off? Well, yeah, of course it does, right? So you could be, for a moment, as you're moving through systemic capillary beds, still carrying oxygen, and carbon dioxide could have gotten on, okay? So they don't outcompete one another, and that's important for you to understand. Everybody okay with that? Okay, and then the other 70% requires you to work through something with me to show you how you carry the other 70%. And it's really this equation. So here's what your red blood cells are going to do for you, okay? And the big picture understanding of this. Ready? Your red blood cells are going to, at your systemic capillaries, force this chemical equation this direction because they have a whole bunch of that carbonic anhydrase enzyme right there, okay? So, and then they're going to pick what they do with each of these. If you hold on to this inside the red blood cell, will it impact the pH of the blood plasma? No. If it's not in solution, it doesn't impact pH, right? And then you could, for instance, dump this into the blood plasma to buffer whatever pH changes were there. If you do this, you force this equation this way and hold on to this, you can carry massive quantities of carbon dioxide with minor changes in pH. That's the big picture understanding. Does that make sense to you guys? So let me show you how it works. Ready? Okay. So we're going to go all the way from the beginning. Stop me if you get confused. You ready? Okay. Carbon dioxide was generated via cellular respiration, yes? 7% just travels in the bloodstream as carbon dioxide. 23% sits on a different seat on the hemoglobin bus, yes? The globin portion of hemoglobin. But the other 70% does this. Follow with me. Carbon dioxide right here, plus water, which is ubiquitous. You have it everywhere, right? Via carbonic anhydrase, that's the enzyme that does this equation, goes to the carbonic acid right here, okay? This part you need to pay attention to. Carbonic acid dissociates into HCO3-, the bicarbonate ion, and H+. Now, what I have is H+, but I'm not going to let go of it. I'm going to keep it inside the red blood cell, and I'm going to loosely and reversibly bind it to the globin portion of hemoglobin. Basically, what I'm going to do is, it is positively charged. I'm just going to stick it temporarily to a negatively charged amino acid. If I do that, it doesn't go into solution and it doesn't impact pH. Does that make sense? So, and then what I'm going to do is whatever pH changes already occurred in the blood plasma, I can help them if I put that buffer out into the blood plasma. Yes? I put bicarbonate ion into the blood plasma to give it extra buffering capacity. But what I have to do in order to dump a whole bunch of bicarbonate out without affecting the electrochemical gradient of the red blood cell is every time I push a negative out, I temporarily bring a negative in, okay? So what I do is I have this little co-transport or counter-transport protein right there. I bring chloride in, negative, right? I push bicarbonate out, and I'm just holding on to the chloride for a minute, okay? Right? So this is called the chloride shift, okay? So before I go any further, I want somebody to tell me in your words What is the point of all of this? What the hell are you trying to do here? Just confuse people at the end of the semester? Is that what you're trying to do? What's the point? Regulate your blood pH, yeah? So what am I doing? What am I effectively doing here? I'm carrying what without affecting what? Carrying massive quantities of carbon dioxide with very minor changes in pH. Do you see? Okay, all right. So to reinforce that, of course, I want to go ahead and tell you that you can't breathe out bicarbonate ion, even though, of course, you're carrying 70% of your carbon dioxide as bicarbonate ion. So now what I'm going to have to do is deliver that blood with really minor changes in pH, right? I'm going to have to deliver it back to the lungs. And what do you predict I'm going to have to do in order to get rid of the carbon dioxide? You're going to have to blow it out, but what are you going to have to do first? Yeah, you're going to have to reverse everything that you just did, yes? Okay, so let's see what is actually going to happen when you do this. So here I am at pulmonary capillary beds. Again, I want you to make sure that this makes sense to you. Of the 7, 23, and 70, what's the easiest one to get rid of? The 7, because it was just dissolved in the blood plasma. Breathe that out first, right? What's next easiest to get rid of? The 23 that was bound loosely and reversibly to the globin portion of hemoglobin, right? Okay, get rid of that first. And now I've got the 70%. And in order to get rid of the 70%, I'm going to have to do everything in reverse. You ready to do everything in reverse? Okay, so what I'm going to have to do first is I'm going to have to get the bicarbonate back in, right? Okay, I'm going to reverse the chloride shift. I'm going to put chloride back out into the blood plasma, and I'm going to bring bicarbonate back from the plasma into the red blood cell. You with me? Okay, where do I get the H+? What was holding on to it? Yeah, one of the amino acids on hemoglobin, right? So hemoglobin was holding on temporarily to the H+. Give it back, right? And now I am going to shift this equation this direction, right? So now I'm going from here to here. Yes? I form carbonic acid. And this enzyme, by the way, can do both chemical reactions. It can do it either way. So this one, via carbonic anhydrase, is going to get pushed this direction. I'm going to dissociate to carbon dioxide and water. I don't care what happens to the water, do you? No, right? And then I'm going to breathe out the carbon dioxide. That make sense? Okay, so although this looks confusing as hell, this is why I taught you this freaking equation early in the semester. Because by now, it should kind of be second nature to you to understand this equation, right? So we actually do this equation in 2 different places, right? Remember that we did it in the kidney tubules too? And the kidneys were trying to regulate pH by controlling this equation. And now I'm telling you, we do it in the red blood cells as well, right? So we're doing this equation. This equation is our primary mechanism for controlling pH in the body, okay? All right, so here's the question though. What is it that determines which direction this equation goes? It's simply the concentration of carbon dioxide. If the PCO2 is high, it tends to shift the equation this direction, which should be true at which capillary beds? Systemic, right? And if the PCO2 is low, it tends to shift the equation that direction, which should be true at the pulmonary capillary beds. Does that make sense? So FYI, they call this hypercapnia when it's high. PCO2 is high, it's hypercapnia. And PCO2 is low, it's hypocapnia. Okay, so now let's talk about how you can alter your PCO2. So the primary mechanism that you use to alter PCO2 is, well, you don't change your rate of cellular respiration just to alter your PCO2, right? Because you got crap to do, and cellular respiration is really important. So the primary way that you can manipulate your level of PCO2 is simply by breathing, right? And changing your rate of ventilation. Does that make sense? Yeah? Okay, so I just want to talk about this whole relationship before we go on to control of ventilation and respiration. Okay, so the primary way that you can alter your PCO2 is by increasing or decreasing your rate of ventilation. So let's talk about this for just a second. If you hyperventilate, which by the way doesn't mean that it's too high, it just means that it's higher than normal, right? If you hyperventilate, what is happening is you are going to be blowing off excessive amounts of carbon dioxide. But here's something counterintuitive that people, myself included, misunderstand. So here's the deal. If I hyperventilate, of course, I'm breathing more oxygen in and more carbon dioxide out, and more oxygen in and more carbon dioxide out, right? But really what I'm actually doing is bringing more carbon dioxide out because oxygen doesn't move in any faster if I don't need it, right? So what I'm really doing is, a lot of people think if I'm breathing really quickly, what I'm going to do is be blowing off carbon dioxide, but I'm also going to be increasing the rate of cellular respiration. But you don't increase the rate of cellular respiration just because you're breathing faster, right? If you don't need it to be any faster, then you don't make it any faster, right? So primarily what ventilation is doing most directly is altering your PCO2, right? It's not right? It's altering the rate of carbon dioxide, the amount of carbon dioxide that you blow off. Okay, so let's think about this. If you increase ventilation, hyperventilation, then what you're going to be doing is you're going to blow off more carbon dioxide than normal. Yes? What will that do to your pH if you get rid of too much carbon dioxide? Should it decrease it? It's going to increase it. Yeah? Because more carbon dioxide drops your pH, yes? Less carbon dioxide will raise your pH. What that can lead to is called respiratory alkalosis, in which your respiratory system is the reason that your blood becomes slightly alkaline, okay? Which is why your mom told you that when you were freaking the hell out, she told you to breathe into a paper bag. Why was mom partially right? Because you breathe more CO2 back in, right? More than is in the atmosphere is in the paper bag. And when you breathe it back in, what does it do? It helps to reset your pH, yes? Okay? So why did mom not tell you to breathe into a plastic bag? Because she wasn't trying to kill you, right? Yes, it would be really effective for concentrating the carbon dioxide, but it would also drop the oxygen to zero really quickly. So is there some truth to that? Yeah, there is some truth to that. The breathing into a paper bag when you're hyperventilating can help. It also can give you something to concentrate on other than what's causing you to hyperventilate. Okay, so the other thing is also true. Let's think about this. If you have a patient with some kind of obstructive breathing disorder like COPD, or you've got a patient with pneumonia, right? In which you can't either do ventilation or gas exchange and you can't get rid of your carbon dioxide effectively. Does that make sense? Can you see that that could cause respiratory acidosis? Acidosis, right? And why? Because you're retaining too much carbon dioxide and forcing it this direction. Is everybody okay with that? Okay. Is that as easy to treat as breathing into a paper bag? It's definitely not as easy to treat as breathing into a paper bag. Does that make sense? And it's one of the reasons that respiratory disorders can shut down whole body systems. So it's not directly related to oxygen. It's primarily related, it's like, this is one of your major mechanisms to regulate your body pH, and it's failing you, right? And then the shape of all of your proteins start to change, for instance, okay? All right, so last thing to do, and this is pretty easy, is just to talk about how you control ventilation to control respiration, right? To control ventilation to control respiration. Everybody okay with that? Okay, so here's the deal. What we have is we have nervous system control of ventilation, yeah? And the nervous system control of ventilation, I don't know if you guys remember from anatomy, but the respiratory centers are in the pons and the medulla oblongata. Those are the ones that are primarily in control of your breathing. But conceptually, you also know that your cerebral cortex can override that, because I can choose right now to hold my breath, right? Or I could choose to breathe more quickly. So what happens is this unconscious, subconscious, below conscious portion of the brain, older than the cerebral cortex, has an inherent rate at which it sends out a stimulus to control inspiration. And luckily that happens without you thinking about it. Otherwise you would die every time you fell asleep, right? Okay. So these guys right here are controlled from the medulla oblongata. So here's what happens. You have these inspiratory neurons that are located in the medulla oblongata. And what happens is they are inherently excitable and rhythmic, and they send out a rhythmic action potential down to the diaphragm via the phrenic nerves, yeah? And down to the external intercostal muscles via the intercostal nerves, right? If you're talking about normal tidal breathing, what happens is they send it rhythmically, and what they do is they send continuous action potentials for about 2 seconds at rest. We're talking about resting tidal breathing, like when you're sleeping, for instance. And then they send continuous action potentials because when you breathe in, you don't just want to go, right? You want to actually get a decent breath. So they send continuous action potentials to get a nice, strong diaphragm contraction and nice, strong external intercostal muscle contraction. And then the stimulus shuts off after about 2 seconds, no more action potentials. And then do you need to do anything to cause expiration? No, just stop, right? And then what will happen is elastic recoil of the lungs, relaxation of the diaphragm, relaxation of the external intercostals. So really, what your medulla oblongata and the pons are controlling is inspiration. Yeah? That makes sense? And expiration is primarily just not doing anything to the muscles, right? Okay? And what about forced expiration? Is that rhythmic? No, it's as needed, right? Forced expiration is basically because either my cerebral cortex decides I need to do it, or I'm really, really breathing hard because I'm exercising, right? And then the expiratory neurons will come online if necessary. And what those will do is they'll only send action potentials during high levels of ventilation or forced expiration. And then they'll send an impulse via the intercostal nerves to the internal intercostal muscles, yeah? And squish the ribs together to do forced expiration. Simultaneously, by the way, not directly related to respiration, but indirectly, they'll also contract the abdominal muscles so that you can push on the diaphragm from the bottom, right? So one of these works all the time, and one of them only works when necessary, right? That makes sense? Okay, so, but of course, we've been humans long enough to know that the rhythmicity is controllable by several different things. One of them is that you have some level of voluntary control over your respiration, right? Because these are skeletal muscles, right? And I have a cerebral cortex that in most circumstances has some level of control over skeletal muscles, right? In addition, have you ever gotten so damn upset that you're like breathing super duper hard like your kids do? You're like, so we have higher portions of the brain than the medulla oblongata and the pons, right? The highest, arguably, is the cerebral cortex, right? That's our voluntary conscious portion. But also the hypothalamus and the limbic system, the emotional centers of the brain. What those can do is they can override the rhythmicity of the pons on the medulla oblongata, right? So I can say, I want to breathe differently with my cerebral cortex, right? And it can go, or I can cry my eyeballs out, get super upset, and those emotional centers will override what the pons and medulla oblongata is doing. Does that make sense? Okay. So we have those. Those are higher brain centers. And then don't be at all surprised that we are also monitoring the chemical content of the blood. And even more importantly, we are monitoring the chemical content of the cerebrospinal fluid. Okay, so there are chemicals that can modify breathing as well. So let's go through these. Although it is counterintuitive, the most powerful respiratory stimulant is actually not oxygen, and it's not pH. It's actually carbon dioxide for reasons that will become obvious in just a second. So here's the deal. Okay, so stick with me. We actually, if we get into a situation in which the carbon dioxide starts to increase in the bloodstream, right? Do you guys agree that we should probably breathe more if the carbon dioxide tends to increase in the bloodstream? But the real reason that it is so powerful is that your brain isn't protected from high levels of carbon dioxide by the blood-brain barrier because it just diffuses straight into the brain, right? Okay, so here's what we have. We have blood that's going to the brain. Here's the medulla oblongata, right? Okay. And if the carbon dioxide starts to increase, what happens is it just diffuses straight through the blood-brain barrier into the cerebrospinal fluid. And then this damn equation goes on, right? And then what happens is you start to increase or decrease the pH of your brain. And your brain gets pissed about that, right? So your brain has almost zero buffering capacity in the cerebrospinal fluid. So if you impact the pH of the brain, you are going to breathe regardless of what you want to do, right? Okay, but please note that this doesn't mean that the pH of the bloodstream actually diffuses into the brain, right? Because the H plus is not going to diffuse into the brain. The blood-brain barrier will be able to prevent that. It's an ion. You have to transport it on purpose, right? Okay. So I'm not saying that the blood pH directly causes you to breathe, but the PCO2 of the blood, because it diffuses into the brain. These are called central chemoreceptors because they're in your central nervous system. So basically, carbon dioxide pisses off the brain really quickly and will make you breathe, okay? Whether you wanted to or not. Good? You got it? Okay. And then what we also do is we also remember that from the cardiovascular system, do you remember that we were monitoring carbon dioxide and pH and oxygen content here in the carotid sinus and here in the aortic arch, right? We already had those receptors. Now, does it surprise you at all that the sensory input from those receptors, in addition to being able to activate the cardiovascular system, can also activate the respiratory system? Does that make sense? Okay, so if you detected, for instance, let's just go through it here. If you detected low pH right here in the carotid sinus, remember? We said that that would probably increase your sympathetic nervous system and increase your cardiac output, right? That makes sense? Okay. Does it surprise you at all that if you detect low pH there as well, right, it will also activate your respiratory system, right? Okay, so it's the same sensory input with a different motor output, right, to fix the problem. So let's look at that one. Okay, so the other ones, the other respiratory stimulant is via the carotid sinus and the aortic arch, and these are called peripheral chemoreceptors, just like they were before. So the pH of the blood, H plus doesn't diffuse directly into the brain, so it's not going to activate the medulla oblongata directly, but what it will do is activate these peripheral chemoreceptors. And what happens is if you detect low pH here, it will send the impulse, and then the medulla oblongata and the pons, the motor output will be to increase respiration. But this one isn't as powerful or as quick to cause a response as this one. Okay, and then, although it's really counterintuitive, the very last thing that can cause an increase in respiration rate is actually low PO2. So you're super sensitive to carbon dioxide, yeah? You're a little less sensitive to pH, and you are least sensitive to oxygen. Because if you don't have enough oxygen, you can just sit down, right? You're like, just stop doing all that crap that you're doing. Stop with all the cellular respiration. So the PO2 is really interesting because it doesn't have much of an effect on breathing until it's super duper low. And it's detected here, right? But it won't impact your breathing at all until it drops below about 60 millimeters of mercury, and then it will increase your respiration rate. Okay? So in order, the things that will cause you to breathe the fastest, or cause an increase in respiration rate the fastest, I should say, are an increase in PCO2, you with me? A decrease in pH, or a decrease in PO2. Okay? So I want you guys to help me put together a story. So think about all this. You ready? Okay. My daughter, who is now 17, when she was 4, she's my stepdaughter, but I've had her since she was 1.5. She wanted a pony at Toys R Us, and it was basically like this big $400 step stool that wagged its tail, and I wouldn't get it to her. And she told me at Toys R Us that she was going to hold her breath to death until I gave it to her. So what I want you guys to do is work through with me what happened. She's alive now, and she doesn't have a pony. What happened that made that threat not work? Okay, so she holds her breath, right? Okay, because her cerebral cortex can voluntarily control her respiration rate. But in a couple minutes, she started breathing, and I want you guys to work through with me how that happened. Why did she start breathing despite herself? Back up a little bit. Before the cerebrospinal fluid gets a high pH, what actually happened? She's holding her breath. What? She overrode the system. She overrode the system, but I want you to tell me how her body overrode her cerebral cortex and made her breathe. What happened?
One of the chemoreceptors.
Chemoreceptors are second. What's the first thing that's going to happen? Work through it. I'm going to wait for you. So she's holding her breath. I told you what the most powerful respiratory stimulant is. What is it? Okay, so she held her breath, and what started to happen to her carbon dioxide concentration? Increase. And then what did it do? Increase the pH of where? What's the big issue here that she ran into? It diffused into her cerebrospinal fluid, right? Right? It dissociated to make H plus in her cerebrospinal fluid. And it pissed off which portion of her brain? Pissed off her medulla oblongata. And then the medulla oblongata, tell me how inspiration starts. Tell me how it sent out the signal to make Savannah breathe. Where? Action potential down what? Phrenic nerves, yes. And external intercostals, and cause what to occur? Contraction, right? Drop the pressure below atmospheric pressure. And then air moved in, right? Despite what she said. So, can you hold your breath to death? No, because your brain will not let you. And I was nice and told her how that worked. As I did not buy her the pony, at which point she told me, I hate you, you're not my real mom. And I was like, you know what, I'm smarter than your real mom, so it's fine. Which is totally true. Okay, everybody good?